This next lecture is on the topic of resonance. Every object has a natural frequency at which it vibrates most easily, and this frequency is called the resonant frequency. You can picture this if you think of pushing a child on a swing. If you push the child with the same frequency as the natural frequency of the swing, then you'll end up having a very kind of smooth sort of flow as the child kind of is pushed right at the point where they would get the most speed forward. And if you push a little bit too fast, you start to notice that the swing doesn't swing back as nicely. It's kind of hard to describe in a sense, but if you can kind of physically imagine that, you might understand what resonant frequency is. It's the frequency at which a medium vibrates most easily. You may have used this technique if you were rocking a car that was stuck in the snow as well. You don't push as hard as you possibly can to try to get the car moving, but you push the car so that the chassis of the car moves forward, and then as it moves back, you push right when it's starting to move forward again. This increases the amount of or the force that you need to get this car to start moving. And resonance is a response of an object that is free to vibrate to a periodic force with the same frequency as the natural force of the object. So you can copy that definition down as well. That's how we can define resonance in this case. When one object vibrates in resonance with another, so if we have two objects that are vibrating with this together with the same vibration, it's called sympathetic vibration. And there's lots of instances of sympathetic vibration. Some of these are useful and some of these are not useful, however. Mechanical resonance must be taken into account when designing bridges, airplane propellers, helicopter rotor blades, turbines for jet engines, plumbing systems, and many other types of equipment. A dangerous resonant condition may result if this is not done. We could also see resonance with things that are moving vertically upward. Rockets can have longitudinal vibrations during launch. And during launch, the propeller pipes can experience a low-frequency disturbance, which periodically changes the propellant flow rate. What we end up seeing is what's called a Pogo Effect. So if you can imagine a rocket trying to, it's accelerating with a great amount of energy off the ground. We could end up having a resonance occurring in the longitudinal direction of the rocket, where it gets compressed and stretched in such a way that it actually seems to go up at a fast rate and then slow down and then go back faster. So it has this pogo effect, kind of like the back and forth flow of a pogo stick. Bridges. If you know anybody who is in the military or in cadets, one of the orders is when you walk across the bridge to walk at a normal kind of pace, not to march, because something happened in 1841 when a troop of British soldiers marched in step across the bridge, and because they were all stepping at the same time, it caused a periodic force that set the bridge in resonant vibration, and eventually the bridge started to collapse. Buildings can also vibrate as well, and one of the ways we counteract this is through the design of large dampers, and we'll get into damping soon. A large building will sort of flow in the air with the wind, and it will kind of vibrate back and forth. This is called aerostatic flutter. And it occurs when more energy is added to the vibrations than can be lost to the natural dampening of the structure. So we would expect a building to lose its resonant energy through damping, and that damping would occur because it's naturally connected to the ground, so it'll lose that energy to the ground. If it doesn't, though, then it will kind of flutter back and forth. So we need to have dampers on the building, in its ground floor, in order to help counteract the aerostatic flutter. It's possible for a singer to sing a note with the same natural frequency as that of a wine glass. And if that happens, the glass could vibrate in resonance with the sound. And if it's high intensity sound, it could actually break the wine glass. If you've ever wondered how your tuner works on your radio, what you're essentially doing is you are setting the antenna the electrons in the antenna. You're setting them to vibrate at a specific frequency, and if that frequency matches the frequency of the electromagnetic radio waves that are flowing through the air, you will pick up that radio signal. That signal will be amplified because the electrons in your antenna are vibrating at the same rate as the radio signal. The human body also has resonant frequencies, and experience has shown that the entire body has a mechanical resonance frequency of about 6 Hz. The resonance frequency of the head is between 13 Hz and 20 Hz. Resonant frequency of the eyes is 35 Hz to 75 Hz. Large amplitude vibrations of any of these frequencies could irritate or even damage parts of the body. For these reasons, engineers are careful to avoid situations where resonance might occur within structures. They must be carefully analyzed to determine their resonant frequencies, and they have to come up with ways to counteract this. And what you see here is a series of stills from video about the Tacoma Narrows Bridge collapse. If you're interested, you can look that up on YouTube. Basically, the bridge started to flow with its resonant frequency, and due to a lot of wind. And once it started into its pattern of its resonant frequency, it caused the bridge to collapse. So that was a disastrous kind of situation, and it was due to the bridge not having any kind of dampers. Here's some things you can copy down for mechanical resonance. You will be having some explain type questions for these tests and quizzes in this unit. So it would be important to know how to answer that. Now, I talked about damping a bit. Damping is the reduction in amplitude of any waveform. It usually involves energy absorption. So when we have a child on a swing, you can imagine that the child will not move forever. Eventually, the energy in the child swing system will be dissipated through friction or air resistance, and we'll end up having the swing slow down in motion until it's been fully damped. In a situation where we are undamped, you would have a constant sort of a waveform that would last forever, and it would not stop. It would not lose energy to any source. That would be an undamped situation. A damped situation looks more like this, where we end up having our energy lost over time. So write this down for damping. It's a condition in which the amplitude of a wave is reduced. Two methods are used. The medium removes energy from the wave, or destructive interference reduces its amplitude. To help increase the amplitude of vibrations due to resonance, some buildings have a mass damper, as I was mentioning earlier, usually consisting of large shock absorbers or a pendulum made of concrete or steel. These dampers develop sympathetic vibrations which take energy from the building when it vibrates, thus decreasing its amplitude.